Example 1, using an exponential growth function, math for Mr. Williams. The inaugural attendance of an annual music festival is 150,000. The attendance Y increases by 8% each year. Write an exponential growth function that represents the attendance after t years. Alright, so the first thing we need to identify is the initial amount, and here we have it at 150,000. Then we identify the growth rate. In this case, it is growing, not decaying. And that amount will be about 8%. And then time, we don't know yet, so we're going to go ahead and give that the letter t, because that's what they're asking for. Now let's go ahead and set up our function. So we have y equals our initial amount of 150,000. Now that's going to be multiplied to our growth rate. In this case, we don't want to put 8%. We know we have to add that to 100%. So I'm going to show that here. This is our initial amount plus 8%, give us 108%. Now we're going to go ahead and move our decimal over to make it a decimal, giving us 1.08 for our b value, and then t as our exponent for time. All right, on to b. It says about how many people will attend the festival in the 5th year. Now, a couple things to remember here. They're looking for 8 bouts, so we don't have to be very exact. And the 5th year, and remember that the value t equals 4 represents the actual 5th year, because t equals 0 represents that first year or that initial amount. So in other words, if I put 0 in for the t, I'm going to get that 150,000. The next year would be worth 1. That would be the 2nd year, and so on. So we write out our exponential function. We substitute that 4 in for the t. We compute our answer, and we arrive at 204,073 people. So since our question is asking about 204,000 people will attend the festival in the 5th year. Example 2, using an exponential growth function, math of Mr. Williams. Website has 500,000 members in 2020. The number y of the members increases by 15% each year. Write an initial growth function that represents the website membership t years after 2020. So let's go ahead and start off with that initial amount. We can see that's going to be represented by the 500,000. Now let's go to the growth rate. We can see that's going to be the 15%. And now let's deal with the time. We can see that's going to be represented by the t for years. Let's go ahead and plug in our function. Y equals our initial amount of 500,000 times our b value, or our growth rate added to 100%. That'll give us 115%. Now we move our decimal 2 times. 1, 2, giving our decimal version of 1.15 for our b value. And then we plug in our exponent of t for time. All right, next question. About how many members will there be in 2026? Well, first let's figure out that time-wise, the t. So we know our initial value would be 0, and that would be represented by 2020. So 1 would be 2021, 2, 2022, and we have 3, 4, 5, and 6. So this is 22, 23, 24, 25, and 26. So we're looking at t being worth 6. So 6 years in. So the value t equals 6 represents the year 2026, because t equals the 0 represents the year 2020. So we're going to write our exponential growth function. We're going to substitute that 6 in for the t. We compute it, and we see that it comes out to 1,156,530 people. All right, so we round to our significant digits. So the website membership will be about 1,160,000 people in 2026. Example 3, identifying exponential growth and decay, math, Mr. Williams. Determine whether each table represents an exponential growth function, an exponential decay function, or neither. Explain. All right, so let's go ahead and take a look at A. So we start with our x value. We can see that it is increasing by 1 each time. All right, but we can see our y value is decreasing each time. So the real question is it being subtracted each time or is it being multiplied by a fraction? So let's see here. We can see that 270 down to 90 is going to be about minus 180. 90 down to 30 is going to be subtracting 60. 30 down to 10 will be subtracting 20. So there's no common subtraction there. So it's going to see about multiplication. So we can see to find that multiplication, we're going to take the one we're going to and dividing it by the one we're coming from. So in this case, we're going to have 90 divided by 270, and then we'll have 30 divided by 90, then we'll have 10 divided by 30. We can see when we simplify those, that'll be 1/3 each time. So we can see that we are actually multiplying by a fraction, which means we are decreasing. So this is a decay function. All right, on to B. We check our x values again. We see that they are increasing by 1 each time. Now let's check the bottom, the y's. How do I get from 5 to 10? Well, I could add 5. But as soon as I see this one right here, 10 to 20, I can see that's a 10. All right, so there is no common addition going on here. The 20 to 40 is going to increase by 20. So let's go ahead and use our same principle here. We're going to take the one we're going to, and we're going to divide it by the one we're coming from. So in this case, it's 10 divided by 5, 20 divided by 10, 40 divided by 20. We end up with times 2 each time. So this, in this case, is going to be an exponential growth model. Example 4, identifying exponential growth and decay. Math of Mr. Williams. Determine whether each table represents an exponential growth function, an exponential decay function, or neither, and explain. All right, let's take a look at the first one. So we go from 0 to 1 to 2 to 3. You see that x value is increasing by 1 each time. All right, so the y value we see is decreasing. So the question is it being subtracted each time, or is it being multiplied by a fraction? So in this case, let's go ahead and assume that it's going to be multiplied by a fraction. So we're going to go from the one we're going to over the one we're coming from. So let's see, here we have 16 divided by 64. And then we're going to have 4 divided by 16. Then we're going to have 1 divided by 4. Now I can quickly see that 1/4 looks like it's already simplified. So let's see, what can we divide in each one of these? We divide this guy by 4 on top and bottom, and we can divide top and bottom on the first one by 16, giving us 1/4 as our multiplier all the way across our table. Okay, so this is going to be an exponential decay function. All right, on to the second one. We can see our x values are increasing by 2 each time. All right, so then we take a look at our y values. We can see that these y values looks like they're going up pretty steady. Let's see. So since they're increasing, we're only checking really addition, or we're checking for multiplication. So from 4 up to 11, we're going to add 7. From 11 to 18, we're going to add another 7. From 18 up to 25, we are going to add another 7. So this is neither exponential decay or growth. This is actually going to be a linear situation. So this answer is neither, because it is linear. Example 5, interpreting exponential functions. Math of Mr. Williams. Determine whether each function represents exponential growth or exponential decay. Identify the percent rate of change. So the first one we have y equals 5 times 1.07 to the t power. All right, so because that 1.07 is greater than 1, the function represents an exponential growth function. The growth factor, 1 plus r, is equal to 1.07, so you can determine that the r value is 0.07. So the function represents exponential growth, and the growth rate is 7%. All right, for b, we have f of t equals 2/10 plus 98/100 to the t power. So because the 98/100 is between 0 and 1, the function represents an exponential decay problem. The decay factor 1 minus r is equal to 98/100, so you can determine that the r is equal to 200. So the function represents exponential decay with the rate of decay that is 2%.